In a prior video, I described problems with the Milstein Hall below-grade gallery due to water entering the concrete slab above the gallery space and working its way through the concrete fascia and onto the gallery windows. These problems, as it turns out, were the result of numerous errors in the design of the plaza deck slab that forms the roof of the gallery space. Such a slab deck is really a roof, and as Joseph Listerburg wrote back in 2011, it needs to be designed as a roof with the following 6 characteristics. 1. The design must provide drainage below the traffic surface, including a drainage gap above the water control layer that is above the roof membrane. 2. The roof membrane must slope to a drain. 3. The design should really incorporate a double drain, that is a second drain from the traffic surface. 4. Insulation should be installed above the roof membrane with a drainage mat above and below it. 5. All drainage should slope away from the edge of the deck towards an interior drain. And 6. The water control layer of the deck must be connected to the water control layer in the walls of any adjacent existing buildings, Sibley Hall, for example. Of course, the load-bearing brick wall of Sibley Hall has no water control membrane, so it is important and difficult to properly flash this wall deck intersection. Of these 6 guidelines, only one was properly implemented, the one requiring insulation above the roof membrane with drainage mats above and below the insulation. From these old construction video clips that I took previously, we can see the drainage mats and insulation being placed above a perfectly flat structural slab, and then a topping slab, also perfectly flat, being placed above the insulation and drainage mat. The other 5 requirements for a slab deck over heated space were simply not specified in the design drawings and therefore were not implemented. There was no explicit drainage gap below the traffic surface. Not only was the deck designed with no slope, but there was no drain specified for the plaza. And with no drain specified, of course, there could be no double drain. Because the water control layer did not slope, and therefore did not slope away from the edge of the deck, water was able to enter the fascia above the gallery windows and threaten the integrity of the concrete while staining the windows below. And finally, the intersection of the roof membrane and the brick wall of Sibley Hall was not properly flashed. As it turned out, there was also an additional problem with the structural design of the slab deck itself. However, this very problem of slab deflection actually allowed Cornell to retroactively address 2 of the major mistakes from the original design. Because of the unintended sloping of the deck, it became possible to install a new drain at the low point of the deflected slab, which would slope away from the edge of the deck. This still leaves a couple of the guidelines unaddressed, but by installing a drain and by rebuilding the fascia edge with new flashing and drip edges, the main problems appear to have been remediated. So, here's what was done in the summer of 2015. First, the topping slab was cut and most of the insulation was removed to accommodate a linear channel sloping to a new drain. The trick was to thread the drain pipe down through the gallery below. The drain location was therefore aligned with the gallery wall below. The new pipe goes through the gallery wall and into the gallery slab, which was ripped up and replaced with new concrete, where it is connected to a storm sewer pipe below grade that happened to be in the vicinity. Next, concrete was placed in the slot. The metal drain sections are prepared and assembled. These metal channels direct water into the actual drain and are aligned and held in place with gobs of concrete. A cover plate fits over the half cylinders to provide a thin inlet for surface water. The whole assembly will be inaccessible once the final concrete is cast, so there is a clean out at the far end, and a stainless steel cover plate over the drain itself. Finished concrete is now cast against the metal inlet, and the surface is finished to match the adjacent concrete. One can see that when it rains, the new drain doesn't exactly capture all the surface water. Puddles always remain because a slope was never actually built into the original design. Meanwhile, additional reconstruction needs to happen at the edges of the plaza, over the gallery windows, and on the western edge near Sibley Hall. Workers use concrete saws and jackhammers to remove most of the perimeter fascia above the gallery windows. Metal rods are inserted. They will be used to fasten wooden formwork so that concrete can be replaced where it has been removed. A metal drip edge is installed over the one previously installed during the first reconstruction of this gallery that proved ineffective. A rainwater membrane is joined to flashing, new insulation is placed over this new air-water barrier, and workers now cut the metal threaded rods fastened to those already attached previously. Then another piece of stainless steel flashing is installed over the drip edge, and water presumably is intended to go between these two pieces of metal. Here we see the formwork with a slot for casting the concrete, and the concrete at this point has been cast and the formwork removed, all patched up and ready to go. The new drip edge is visible. Finally, sealant is placed in the biggest cracks, since any water that penetrates the surface of the concrete still has a good chance of doing some damage below. At Sibley Hall, a similar process is undertaken. First, part of the slab deck is removed, revealing rather inadequate flashing, especially given the cracks in the existing brick wall of Sibley Hall, which can allow water to enter Milstein Hall by getting behind the flashing. Similar concrete work is performed on the fascia with the same type of waterproofing and the same metal rods for formwork. And eventually, more slab is removed, new waterproofing is flashed a bit higher into the existing wall. We see a temporary guard put into place with the fascia repaired. So, to summarize the problem and solution, we start with the slab deck as designed. Then we show, schematically, the structural deflection of the slab. Water that penetrates through the topping slab or walking surface fills up the drainage mat under the insulation since it has no other place to go. Eventually, it exceeds the storage capacity of the drainage mat and works its way over the edge and onto the gallery windows. Such water also compromises the effectiveness of the insulation and threatens the integrity of the concrete. The solution, while not ideal, has two parts. First, a more robust drip edge is created over the gallery windows by removing the concrete fascia, installing stainless steel flashing that is then adhered to a new air-water vapor barrier or control layer, replacing the rigid insulation, adding a second piece of flashing so that any water that gets through will be able to exit under the new concrete. Finally, sealant is placed at the locations where water can most easily enter the slab. The second part of the solution is to install a new drain at the approximate low point of the slab, a low point that was unintended in the original design, but that was created by unwanted slab deflection. Then, if any water penetrates the topping slab, it will most likely work its way to the new drain. If not, it has a new pathway out through the stainless steel drip edges on the fascia.